Alright, so now that we've worked out how to do basic derivatives of polynomials, we're going to have a look at some applications of what we can actually do with it. So for this question, we're just going to find a derivative at a specific x value. So for f of x, let's find f dash of 2. So first of all, let's just find f dash of x. Now, since it's not asking us to do it from first principles, we can just derive it normally. So bring the 3 down times 2x, 3 minus 1 is 2, minus bring the 2 down times 3, x, 2 minus 1 is 1. And the derivative of 4x is just 4, and the derivative of negative 1 is 0. So that's all finished, and we get 6x squared minus 6x plus 4. Alrighty, from here what we can do is now work out what is the value when f dash of x equals 2, or f dash of 2. So substitute 2 in, we get 6 times 2 squared minus 6 times 2 plus 4. We get, first of all, 24 minus 12 plus 4. And here that gives us 24 minus 12 is 12, 12 plus 4 is 16. All right, so that means that the gradient at x equals 2 is 16, or the derivative evaluated at x equals 2 is 16. Alrighty, let's have a look at doing a little bit more. Alrighty, and this time we're going to be using Leibniz notation because we're given a function y equals x to the 3 minus 12x. So first of all, we're looking for dy dx, which is the gradient of y, or the gradient function, or the derivative of y. Bring the 3 down, x to the 2, and minus 12x derives to minus 12. Alrighty, so there's our derivative. For b, we're going to be substituting into dy dx, x equals minus 1, and what do we get? The gradient dy dx is equal to 3 negative 1 squared minus 12. Negative 1 squared is 1, 3 times 1 is just 3, 3 minus 12 is minus 9. Alright, see, determine the coordinates of the point at which dy dx equals 0. Alright, so coordinates means we're looking both for the x coordinate and the y coordinate. So just make sure we remember that. But let's first of all work out what x values we have. Alrighty, so for dy dx equals 0, that means we get 0 is equal to 3x squared minus 12. Because remember, 3x squared minus 12 is our derivative. Alrighty, so let's solve for this. Move the 12 to the other side, 3x squared. Divide both sides by 3. Take the square root. Remembering when we're taking the square root that we always give plus or minus. And so we get two values at 2 and at negative 2. Only problem with this is that it wanted the coordinates. We've only found the x coordinates. To find the y coordinates, we need to go back to the original function and substitute into there. So here's the original function, y, and we're going to substitute in x equals 2. We get 2 to the power of 3 minus 12 times 2, which is 8 minus 24, which is minus 16. So the first point we have is 2 comma negative 16. And the second point is going to be at x equals minus 2. Y is equal to minus 2 to the power of 3 minus 12 times minus 2. We get negative 8 plus 24. In this case we get 16. And so we get y is equal to negative 2, 16. So the 2 points in which the gradient is 0 are 2, negative 16, and negative 2, positive 16. Alrighty, part D asks us to determine the subdomain for which dy dx is greater than 0. So to do this, we've got two options. One is to sketch y, and the other is to sketch dy dx. So this becomes a question. Would we rather sketch this, or would we rather sketch this? Now my answer is I would always rather sketch a polynomial, a lower order polynomial, meaning I'd rather sketch a quadratic over a cubic. So I'm going to be sketching dy dx. So how do I sketch a function like this? Well, it's exactly as I would normally sketch it. I want to find the y-intercept, except it's going to be a dy dx intercept. And I also want to find my x-intercepts, which means I want to factorize it. So let's factorize it. So we get 3x squared minus 4. X squared minus 4 is a difference of perfect squares, so that's 3x plus 2x minus 2. And that is the fully factorized forms, which means that my x-intercepts are going to be 2 and negative 2. And based on the original function, my dy dx intercepts are going to be negative 12. Right, because when x is 0, that's just going to be equal to that. So now I can sketch this function really quickly. Alrighty, so my x-intercepts are at 2 and negative 2. My y-intercept is at negative 12. Sorry, not my y-intercept, my dy dx. For my y-axis is replaced by the gradient axes. And as you can see, it's also a positive quadratic, which means that it's going to be a smiley face, not a frowny face. And I can draw in my function like so. And so the question was, when is dy dx positive? Well, it's positive here and it's positive here. So therefore, we can see that dy dx is greater than 0 when x is greater than 2 or when x is less than negative 2. So sketching is often a really helpful way of working out basic information. Alrighty, let's look at one more example. Determine the gradient's properties of a graph. Alright, so we've got g of x is equal to x minus 3 over x, where x does not equal 0. Determine the gradient of the graph of g at p negative 1, 4. Well, because we're looking for the gradient, we definitely would like to know what g dash of x is. So that's the first thing we're going to do. But we can't currently derive that function. So the first thing we're going to do is we're going to rewrite that function by expanding the denominator. So we get x on x minus 3 on x. The x on x cancels. We get 1 minus 3 on x. And 3 on x we would rather write as 3x to the minus 1. It's going to make our life easier when deriving. Therefore, g dash of x means bring the minus 1 down. Oh, derivative of 1 is nothing. Derivative of minus 3x to the minus 1 is minus 1 times minus 3x to the minus 2. Minus 1 is minus 2. Simplify this, we get positive 3x to the minus 2, or 3 on x squared. Now that doesn't finish the question because it actually wanted us to find the gradient of the graph at the point negative 1, 4. But if we have a look at that, this function only deals with x. So I just need to substitute in the x coordinate, and that's going to be enough. So we're going to get g dash of negative 1 is equal to 3 on negative 1 squared. Negative 1 squared is just 1, and so the gradient is going to be 3. So the gradient at negative 1, 4 is 3. Alrighty, so let's have a look at B. Determine the coordinates of the points where the gradient is equal to 1 over 3. So let's write that in a function notation. So we're wondering when g dash of x is equal to a third. Well, we know what g dash of x is. It's equal to minus 3 on x squared. And we're looking for when it's equal to a third. First thing, flip both functions, both sides. Then multiply both sides by negative 3. So copy error, it should be 3 over x squared. So when we flip it, it becomes x squared over 3. Multiply both sides by 3, and we get 9 is equal to x squared. Take the square root, and we get the answers plus or minus the square root of 9, which is plus or minus 3. So we've got two solutions to this one as well. Now for this one, it wanted not just the x coordinate, it would like the coordinates, which means we need both x and y. We found the two x values, now we need to substitute back into the y function, the g of x function, to figure out the y coordinates. Alrighty, so x is equal to 3, so we're looking for g of 3, and we get 3 minus 3 over 3, which is 0 over 3, which is 0. So the first point is going to be 3, 0. And the second point, x is equal to negative 3. It's going to be g of negative 3. It's equal to negative 3 minus 3 over 3, which is minus 6 over 3, which is minus 2. So the second point is going to be 3 minus 3 minus 2. Alrighty, so there's the coordinates of that point. Alrighty, thanks for watching. See you in the next one.